Hi, everybody. This is Mr. Folly, and welcome to the last part of this answer key. I know you've been dying for it. So let's hop right into it. What is the delta H for the reaction above? So notice here's one where we've got solids and gases we have to deal with. Okay, so the first thing I'm going to do is make my product, which I said before. So I'm going to flip this and have to multiply it by 2 because I'm trying to get this on the right-hand side times 2. So I'm going to have high yields, 2 high yields H2 plus I2. And here the states of matter matter, so I'm going to keep them in there just in case the other ones matter too. And then the other thing is now I want my I solid on the left, and this one is like that, but I want to have a coefficient of 1, and that's a half. So this is just plain old regular times 2. So this is going to be H2 plus I2. This is a solid. Oops, that's not a solid, that's a gas. It's a solid and yields 2 high gas. And I'm going to cancel out 100 gas, and then I have it. So that means this is going to be 52, and this is going to be positive 5 times 10. So that's going to be 62. Notice how it took 62 kilojoules for it to go from low energy to high. It's absorbing it. I'm going to emphasize the positive here. Consider the two compounds below. I'm considering. Which substance has stronger intermolecular forces? Support your answer. F O to H is more polar than what dimeth, not dimeth, dimeth has. So, what intermolecular forces does ethanol have? Ethanol has intermolecular forces of H bonding, and I bet you forgot it, and dipole. What intermolecular forces dimethyl ether have? Okay, so these are all nonpolar parts, but the little bit of O right there makes it polar. So it just has dipole. Oops, I put dipole, and I believe I said dispersion. You don't have to put dipole when you say H bonding, but you do have to put dispersion. Dipole, and dispersion. And that dipole is going to be very weak because it's buried into the nonpolar things. What intermolecular force is responsible for the differences in boiling point? Explain your reason. So it's going to be intermolecular because C to H or C to O, etc., bonds don't break. So if this was a mixture, I should read it again. Oh, I'm just considering two compounds. So what forces would be included? So for ethanol is H bonding and dispersion. And then for dimethyl ether, it would be dipole and dispersion. Explain why carbon-carbon triple bond requires more energy to break than a carbon-carbon single bond. It's stronger and shorter. So Coulomb's law says so. So the radius part is in there. So carbon-carbon single bond longer than, shorter than, or equal in length to a carbon-carbon double bond. Single is longer. Define bond association energy, also known as bond enthalpy. Energy to break a bond. By the way, that will always be positive. Why are bond association energy positive? Energy is absorbed in bond breaking. A certain bond is bond enthalpy of 125 kilojoules per mole. How much energy required to break the bond? Okay, I'm going to guess if it is a bond, it is 100. It is, well, the bond. If I assume that is 1 mole, that is 125 kilojoules per mole, but I asked a bad question here. So if the bond means a bond, I'm going to say I have 1 bond times 125 kilojoules per 1 mole times 6.02 E23 bonds. And this is shockingly kind of a common question that they do to you. So you have 1 times 125 divided by Avogadro's number. And you get 2.07 E negative 22 kilojoules. Is bond breaking endothermic or exothermic? It's endothermic. Okay. A reaction is exothermic. What can be said about the bond enthalpies of the reactants compared to the bond? So remember, what happens is you break, which is positive, and you're going to combine that with the negative, which is the ones that form. So if my overall answer is exothermic, that's going to be negative. What can be said about the bond enthalpies of the reactants compared to the sum of the bond enthalpy of the products? Reactants are less than products. Remember, these would be my reactants, these would be my products. In the chemical reaction below, it is known that A to, oops, let's put that back on there. In the reaction below, it is known that A to B has a bond enthalpy of 85. A to B. Okay, determine the bond enthalpy of A2. Okay, so what I have here is I have A to A. I have no bonds happening here, right? And then I have an A to B to A. Okay, so what has to happen here is I have to break, I'm going to call that X. And then it's going to be plus bond enthalpy is this. These are forming. 2 times negative 85 equals negative 150. So that positive there just to emphasize that the breaking part. So bust out my calculator. I guess I'll show a little extra work here. X plus 2 times negative 85 plus negative 170. That's going to get rid of that plus sign there so we don't mess it up later. X minus 170 equals negative 150. X equals 20 kilojoules per mole. Kilojoules per mole. Predict the fine. Negative bonds form. Positive break nucleus and electron bond. Positive, you're breaking a bond. All right, bond. Oops, put that back up there. All right, bond to enthalpy values. So here's our table of joy. Let's see how we do with this. Explain why C to C is less than C. So again, we have longer and weaker. Why it would be weaker, it would be fewer electrons attracted to nuclei. So the bond enthalpy HCl is greater than HBr using principles of atomic structure. So that means principles of atomic structure usually means size, right? So chlorine is above bromine. So chlorine, Cl, is smaller, therefore stronger. Determine delta H for the reactions given below. So I have to break. So I have H to H plus Br. Oh, this is going to be this way, huh? To Br. And then I'm going to have minus 2 times H to Br. So H to H is 436 plus Br to Br, 193. minus, again, these are subtracted because they're forming, 2 times h to the r, 2 times h to the r, 2 times h to the r, 366. 2 times 366. So calculate time, 436 plus 193 minus quantity 2 times 366, close quantity, enter, negative 103 kilojoules per mole. All right. I guess it's not kilojoules per mole, it's kilojoules per balance equation. So, for this one, so this is maybe because it's not drawn out as well as it should have been. Okay. So I'm going to have 4 C to H's plus Cl to Cl plus, so again, this is going to be Cl to C, H, 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 negative Cl to C plus 3 times negative C to H plus negative H to Cl. All right, so let's hop back up here. C to H, 413. So 4 times 413 plus Cl to Cl, 242, plus negative Cl to C, probably going to be C to Cl, negative C to Cl, negative 328. So minus 328 plus, and put the minus here, 3 times C to H, that was 413. So I guess that's 3 times 413 plus minus H to Cl, H to Cl, C to Cl, where's H to Cl? H to Cl is 431. So 4 times 413, enter, plus 242, plus negative 328, enter, minus quantity, 3 times 413, close quantity, minus 431 is negative 104. That was weird, wasn't the same one I had before? That would be kilojoules. Use abundance to be values of delta to estimate delta H reaction given the numbers below. So same deal. All right, so this 2 right here means I've got to double all of these, okay? So it's got to be 2. So if I see C to H, uh-oh, this is going to be a problem. Yeah, that's going to rate funny the whole time. I'll try it above here. Let's try it again. 2 C to H, okay. Well, it's going to be 2 times 3, so it's going to be 6 C to H, right? I got 2 of these, 6. And then I'm going to have 2 C to O's plus 2 O to H's, okay? And that's going to be taking care of this. I doubled it because of the coefficients. Plus, I have 1 of these, but times 3, 3 O double O's, plus, and these are going to be negative, so I have 2 here. I have 4 times negative C double O, plus 4, 1, 2, so 8 times negative O to H. And then, it'd be nice that plus sign stayed there, but it won't. I'm not going to write those numbers down. I'm just going to get all kinds of crazy. So I'm going to put it right into my calculator. So what am I doing here first? 6 C to H. So 6 times 413, enter, plus 2 times C to O. Plus quantity, 2 times 358, close quantity, plus C to O, 2 times OH, quantity 2 times OH is 463, plus 3 O double O's, plus quantity 3 times 495 closed quantity plus 4 times negative, good morning, 4 times negative C double O, 4 times, so plus quantity 4 times negative 799 closed quantity plus 8 quantity 8 times negative OH negative 463 close that bad boy, and I get negative 1295. Oh man, I actually think I used that one on the Excel test. I thought it was negative from 1319, but we'll see. This one, just because I don't see any coefficients, I'm going to make sure it's balanced. 3 bromines, carbon, 1 carbon, 1 hydrogen, 2 chlorines, so it's okay. So this is going to be, I'm going to shorten it a little bit. I'm going to do, oops. So I'm going to do 3 times, I'm going to look up right away the CBR. C to BR is 276. 3 times 276. Wow. Or that thing. 3 times 276 plus 1 C to H. C to H, 413. Plus, I got Cl to Cl. On the right hand side, 242. Plus, here I'm going to have a negative CBR3. Okay, so here's CBR3, right? Still the same. So that's going to be plus 3 times negative 276. A C to Cl. I don't have one of those. Plus negative C to Cl. C to Cl is 328. That's C to Cl. And then C to H plus negative 14, 413. Okay, well, my worksheet's not responding, so I might have to take a break here and call this one a last part, part 1. That I will say toodles.